Imagine a world where processing long sentences didn't mean waiting for one word after another. What if you could understand the entire sentence context all at once in parallel?
That sounds like a massive speed up, especially for translation. But I thought sequence models, by definition, processed things in order. Isn't that how they build context?
Before 2017, that was largely true. Dominant models were built on recurrent or convolutional networks. They processed sequences step by step or with limited local context.
Like an RNN updating its hidden state word by word, or a CNN looking at fixed size windows. We covered those in earlier cases, so what changed here?
This paper, Attention is All You Need, proposed a radical shift. They introduced a new architecture, the transformer, that was based solely on attention mechanisms.
Solely? So no recurrence or convolutions at all? That feels like throwing out the rulebook for sequence modeling.
Precisely. We explored the attention mechanism in detail in case TCM 153002. Today, we're building on that, showing how an entire architecture can be constructed from just attention.
So it's not just attention improving existing models, it's attention becoming the foundation itself. What was the big payoff?
The immediate benefit was that these models became more parallelizable and requiring significantly less time to train compared to previous recurrent models. This allowed for unprecedented scaling in training.
Parallel processing for sequences? That's what makes it so fast, right? No more waiting for the previous step to complete.
And it wasn't just speed. The paper showed these models to be superior in quality for machine translation tasks, achieving, for example, 28.4 BLU on the WMT 2014 English to German task, which improved over existing best results by over 2 BLU.
Faster and better? That's a powerful combination. It really highlights the impact of this architectural innovation.
They also quickly found that the transformer generalizes well to other tasks, like constituency parsing. This hinted at its broader potential beyond just translation.
So it wasn't just a niche solution, it was a fundamental shift that applied to different kinds of language problems.
Exactly. This universality is key. In case TCM 213002, we touched on the transformer's modality-agnostic nature. Today, we'll see how this architecture achieves that, moving from language to images.
But how does a model built for words even begin to process images? That's the part I'm curious about. What's the intuition behind it?
Let's start with a high-level view from the illustrated transformer. Think of the transformer as a two-part assembly line for information, an encoder and a decoder. Like an assembly line, it processes information in stages. But unlike a purely sequential one, many parts of the input can be worked on concurrently, with self-attention allowing them to interact.
Okay, like a standard sequence-to-sequence model setup? Taking one sequence and outputting another? Say, English to French translation?
Yes, exactly. The input sentence goes into an encoding component, and the translated output comes from a decoding component. They work together, but have distinct roles.
So the encoder processes the input, and the decoder generates the output. Simple enough as a black box?
But it's not just one encoder and decoder. The paper used a stack of encoders and a corresponding stack of decoders. Each layer processes the output from the layer below, passing it through its own self-attention and feed-forward networks, allowing it to learn more complex, abstract features of the input.
A stack, so deeper layers can learn more abstract features, just like in deep neural networks. 6 layers were used in the original paper, it says here.
Here's the crucial intuition for parallelism. Unlike RNNs, where each word waited its turn, in a transformer, each position flows through its own path.
So if I have a sentence of 10 words, all 10 words are being processed simultaneously? Like 10 parallel workers on an assembly line?
This is accurate for the computational flow, but unlike truly independent workers, these word paths heavily interact and exchange information via the self-attention mechanism. But a big question remains. If all words are processed in parallel, how does the transformer know their order? A sentence's meaning heavily relies on word order, which RNNs inherently captured through their sequential nature.
That's true. Dog bites man is very different from man bites dog. Without recurrence, how is that handled?
That's the analogy, but it's not entirely independent. The source notes there are dependencies between these paths in the self-attention layer. That's where context is built.
Okay, so they're not fully isolated. The self-attention lets them communicate, but still in a way that allows for parallel computation.
Each encoder's input first flows through a self-attention layer. This is where a word looks at all other words in the input to understand its context.
This is the core idea from hashtag TCM153002, where each word queries others using K and V to get a weighted sum. It's what gives the transformer its intelligence.
After self-attention, the output goes into a feed-forward neural network. This part processes each position independently, adding nonlinearity and depth.
So self-attention handles the global context, and the feed-forward network acts like a local processor for each word's refined representation. This local processing is similar to a small expert refining details for each word individually after a global discussion, taking in the contextualized word and transforming it further.
You've got it. The decoder has similar layers, but also an additional attention layer to focus on the encoder's output. Now, let's dig a bit deeper into how these layers actually work together.
So we're going from the high-level components to the specific mathematical operations that enable this parallel context modeling.
All right, let's trace the flow. An encoder receives a list of vectors as input. These are typically word embeddings, giving each word a numerical representation.
So if my sentence has 5 words, I get 5 embedding vectors, one for each word. Each vector carries the semantic meaning of that word.
Yes, but with an important addition. Before a word's embedding vector enters the self-attention layer, we add a special positional embeddings to inject some information about the relative or absolute position of the tokens in the sequence. These are learned or fixed patterns.
So each word vector arriving at the self-attention layer already contains information about both what the word is and where it is in the sentence. That's how sequence order is preserved without being sequential.
When the model processes a word, the self-attention allows it to associate that word with other relevant words in the input. For instance, connecting it to animal in a sentence.
This is critical for resolving ambiguity, something RNNs struggled with over long distances. Self-attention dynamically links distant words.
For each vector, the first step in self-attention is to create 3 vectors from each of them, the query, key, and value vectors. These are learned linear transformations.
Right, the Q, K, and V. We covered this in case number TCM153002. Q asks about content, K describes content, and V is the content itself.
Then, to find out how much a word should attend to others, the score is calculated by taking the dot product of the query of the current word with the key of every other word.
A high dot product means a strong relationship, indicating that those words are highly relevant to each other.
These raw scores are then scaled by the square root of the key vector dimension, which helps stabilize gradients during training, especially for very long sequences. And we pass the result through a softmax operation.
So these softmax scores determine how much attention or focus each word's value vector receives when computing the context for the current word.
The next step is to multiply each value vector by the softmax score. This effectively weights the importance of each word's content based on its relevance.
It's like a weighted average, where the weights come from the QK dot products. This analogy is quite precise. You're literally summing value vectors multiplied by their scalar attention weights. The key difference is that these weights are dynamically computed based on the query key relevance, not fixed.
Finally, we sum up the weighted value vectors. This sum is the output of the self-attention layer for that specific word, embedding its contextual understanding.
So for it was tired, the it vector would be a blend of animal and tired based on their attention scores. This blend is precisely what the weighted sum of value vectors achieves, a new vector that semantically incorporates information from other relevant words, weighted by their importance to it.
Now, what I've just described is one attention head. The transformer doesn't just do this once. It does it multiple times in parallel, using different sets of query, key, and value projection matrices. This is called multi-head attention. And as the paper states, multi-head attention allows the model to jointly attend to information from different representation subspaces at different positions.
So it's like looking at the relationships between words through multiple lenses simultaneously. Each head might focus on a different aspect of relevance.
A common confusion is thinking the feed-forward network also has dependencies, but the exact same feed-forward network is independently applied to each position.
Right, so that's where the pure parallelism comes back. The self-attention provides the context, and the feed-forward layer processes each contextualized word in isolation.
This modularity, attention for global context, feed-forward for local processing, contributes significantly to the transformer's powerful and flexible architecture. But can this architecture, originally designed for language, truly work for images?
That's the big jump. Language is sequential by nature, but an image is a grid of pixels. How do you convert an image into something a transformer can understand?
Despite the transformer's success in NLP, for a while, its applications to computer vision remain limited. Convolutional neural networks, or CNNs, were still king.
I can see why. CNNs are specifically designed for images, with their inductive biases for locality and translational equivariance.
The core challenge for vision was converting an image, which is a 2D grid of pixels, into a sequence of tokens that the transformer could process. The VIT paper, an image is worth 16 by 16 words, solved this elegantly by splitting an image into fixed-size patches, linearly embed each of them, add position embeddings, and feed the resulting sequence of vectors to a standard transformer encoder.
So an image isn't pixels anymore, but a grid of smaller square words, and each of those patches gets flattened into a vector.
Exactly. Each image patch is flattened into a 1D vector. Then, a learnable linear projection maps these raw patch vectors into a higher dimensional embedding space, just like how we get word embeddings. Crucially, to preserve spatial location, we add 2D position embeddings to these patch embeddings.
So the transformer sees a list of abstract patch vectors, each carrying its content and its spatial location. Suddenly, an image looks a lot like a long sentence to the transformer.
And then, this sequence of patch embeddings with their positional information is fed into a standard transformer encoder, identical to the ones used for language. It performs self-attention over all patches to build global context for the image, just like it would for words in a sentence.
That's incredible.
So the same attention mechanism that helps it refer to animal now helps understand how different parts of an image relate to each other. But I remember CNNs had built-in advantages for images. Does the VIT lose that?
That's a very sharp observation, Maya, and it gets to a key, honest limit of VIT. The VIT lacks of some inductive biases inherent to CNNs, such as translation equivariance and locality. This means it doesn't inherently understand that an object shifted slightly is still the same object.
So it's more brute force then. It needs to learn these properties from data rather than having them built into its structure.
Precisely. The paper states that large-scale training is crucial for VIT to perform well, often requiring huge datasets like JFT300M. Without enough data, CNNs still outperformed pure transformers in vision tasks.
So while powerful, it comes with a significant data cost and less inherent architectural advantage when data is scarce. That's a critical trade-off.